Hello my friends, welcome to my Energy Economist channel. In this video, we're gonna talk about nature of offshore discharges, especially produced water and drilling waste. So stay with me. Produced water is the water generated from the oil and gas extraction process. It includes the water native to the producing formation, water injected in the formation to increase reservoir pressure and to sweep oil from the formation, and traces of various well treatment solutions, and the chemicals added during production and the oil-water separation process. The volume of produced water varies over the life cycle of an oil field, typically increasing over time. Formation water, which comprises the bulk of the produced water, is found in the same rock formation as the crude oil and gas, or an adjoining level of the same formation, e.g., below the oil-gas cap. Formation water is classified as meteoric, connate, or mixed. Meteoric water comes from rain water that percolates through bedding planes and permeable layers. Connate water, seawater in which marine sediments were originally deposits, contains chlorides, mainly sodium chloride, and dissolved solids in concentrations often many times greater than common seawater. Mixed water is characterized by both a high chloride and sulfate carbonate bicarbonate content, which suggests multiple origins. Besides its ionic constituents, produced water may also contain dissolved and dispersed organic compounds, including hydrocarbons, oxygen, nitrogen, and sulfur-containing compounds, e.g., carbon dioxide, hydrogen, ammonia, and small quantities of heavy metals. Normally, formation water is low in sulfate ion and may contain significant quantities of calcium and barium. Produced water is usually in a reduced state, and it may have both a significant chemical oxygen demand and biological oxygen demand. Treating chemicals are typically added to produced water and may significantly affect its environmental impact. These chemicals are used to accomplish several functions, including the following most common uses: breaking emulsions to aid in the separation of oil and water, preventing the formation of water-formed scales, controlling the growth of bacteria in the producing wells and production system, aiding in the treating of water to remove oil. The industry magazine World Oil annually publishes a list of chemicals currently used in production treating applications. Specific information on the properties of these materials can be obtained from the suppliers' safety data sheets. Drilling wastes include drilling fluids or muds, and the formation fragments known as cuttings removed in the drilling process. Drilling fluids are suspensions of solids and other materials in a liquid base. The composition and properties of drilling fluids are determined by their functions. Three of the primary functions that drilling muds perform are: lubricating and cooling the drilling bit, maintaining downhole hydrostatic pressure, cleaning out the hole by bringing cuttings to the surface. In order to work, muds must have a high density, a high viscosity, and lubricity. To meet these requirements, the mud contain wetting agents such as barium sulfate or iron oxide to increase the density of the mud, clays, bentonite, etc., or polymers to adjust viscosity and the chemical to increase the mud properties. Drilling fluids fall into one of the three classes based on the fluid comprising the mud: water-based muds, oil-based muds, synthetic-based muds. More than one type of mud may be used in a single well depending on the conditions encountered. A water-based drilling fluid or mud is one in which water is a continuous phase and the suspending medium for solids and other liquids, whether or not oil is present. Water-based drilling muds are relatively inexpensive. Modern formulations are generally not toxic to marine fauna. Discharged cuttings will disperse in the water column. The water in water-based muds can be fresh or salt water. Clays or organic polymers are added to achieve the proper viscosity. Barite is added to achieve the correct mud weight. And other components are added to mud systems to create the desired characteristics. The United States Environmental Protection Agency recognizes 8 generic water-based mud types (OCS) guidelines. Oil-based drilling fluids are ones in which the continuous phase is oil, diesel, mineral, or some other oil. Simplistically, they can be viewed as water-based muds dispersed in oil. One important difference from water-based muds is that viscosity is achieved by emulsification of water in oil as well as through the use of clay. They are also more expensive to use than water-based muds. Oil-based drilling fluids are used to solve drilling problems that water-based muds cannot handle efficiently or at all. Conditions warranting the use of oil-based muds include required thermal stability when drilling high-temperature wells, require specific lubricating characteristics when drilling deviated wells, the ability to reduce stuck pipe or hole washout problems when drilling thick, water-sensitive formations, and drilling through water-soluble formations such as salt. Most offshore wells fall into one or more of these classes. Concerns over the potential toxicity of oil-based drilling fluids led to the development of synthetic-based drilling muds. Synthetic-based muds are drilling fluids that use synthetic organic chemicals principally containing carbon, hydrogen, and oxygen as base fluids. Synthetic-based muds are more expensive than oil-based fluids but are more environmentally benign and have increasingly replaced the old oil-based muds. SBMs have low toxicity because of the elimination of the polynuclear aromatic hydrocarbons. They were also designed to have faster biodegradability, lower bioaccumulation potential, and in some instances less drilling waste volume. This means the discharge of SBM cuttings may be permitted. Like oil-based drilling fluids, synthetic-based fluids are hauled to shore after use to be reprocessed and reused. Drilling fluids are designed to have the required characteristics to aid in the drilling of the well, while at the same time limiting their potential environmental impact. Their potential for environmental impact is partially determined by where they end up in the environmental as well as their intrinsic properties. Water-based mud and the cuttings tend to disperse into the water column on discharge. The dispersion is broken and the solid components slowly settle to the sediment layer at the bottom of the sea. Because of the cuttings are rapidly dispersed and their liquid components diluted, their potential impact should be less than that of oil-based or synthetic muds, but spreads over a much wider area. Cuttings from oil-based mud drilling have oil on their outer surfaces and don't tend to disperse in the water column. The solid components tend to settle rapidly to the bottom and collect in piles under the platforms of drilling rigs. Depending on water depth, free oil on the cuttings tends to rise to the surface of the water and spread over the surface of the water. The environmental impact of the cuttings tends to be highly localized initially and persist over a long time in the sediment and water column immediately above it. In addition to drilling muds, the offshore oil and gas industry uses a number of water-based fluids. These include completion fluids, Becker fluids, workover fluids. Completion fluids are typically solutions of salt in water. They are used to clean out wells after drilling is complete and aid in the setting of downhole equipment. Becker fluids are concentrated salt solutions placed between the tubing and the casing of a well. Their purpose is to hold the pressure on the formation in case the beaker fails. They must have a high density in order to be heavy enough to exert sufficient pressure on the producing formation. Workover fluids such as hydrochloric acid are used in cleaning, repairing, and stimulating wells. Typical operations include washing sand from the tubing or wellbore, fracturing water-formed scales, and corrosion products. The salts used to make these fluids include the cations of sodium, potassium, calcium, barium, and zinc, and the anions of chloride, bromide, and sulfate. Completion fluids can be either transported offshore as water solutions, or alternatively, the solid salt can be taken offshore and the solution prepared on site. Spills of completion fluids can result from broken flow lines on the platform or on boats, or from tank failures. When large volumes of completion fluids are needed, they are generally transported on workboats. In the event that the vessel has an accident, the completion fluids could be released. If you want to learn more about the nature of offshore discharges, you could do so in my book, Economic Study of Oil and Gas Well Drilling, which is published on Amazon. Check it out at the link in the description. Please take a second to hit the like button, hit the subscribe button, and don't forget to also hit the notification bell. Thank you for watching, and goodbye.